Hi, thus far we have only talked about the ionic bond between a metal atom and a non-metal atom. The metal atom wants to give electrons. That is because metals are found in groups 1, 2, or 3. So, group 1 metals have one valence electron, and the only way to become stable is to give away that one electron. Group 2 metals have two valence electrons, so the only way to become stable is to give away those two electrons. Group 3 metals have three valence electrons, so the only way to become stable is to give away those three electrons. Now, as you can see, metals give electrons. Metals give electrons. What about non-metals? Non-metals are found in groups 4, 5, 6, and 7. Okay, we don't talk about group 8 because group 8 elements are noble gases. They are already stable. They are already have a full electronic structure, so they will not participate in chemical bonding. Let's start by looking at group number 7. Group number 7 has 7 valence electrons. Group 7 elements, the halogens, have 7 valence electrons. So the way to become stable, the way to achieve noble octet configuration is to take one more electron. Okay? Take one more electron to become 8. Group 6 has 6 valence electrons. So for 6 valence electrons, they need to take 2 electrons to become 8. Group 5 has 5 valence electrons. So to become stable, it needs to take 3 electrons. And group 4 has 4 electrons, must take 4. Now notice non-metals take electrons. So ionic bond is always a bond between a metal and a non-metal, because only in this situation you have one party, the metal, wanting to give electrons, and the other party, the non-metal, wanting to take electrons. So ionic bond is always a give and a take situation. It is a give and take situation. But what happens if you have two non-metals? Okay, you have two non-metals that you want to bond together. Can you use the ionic bond? You can't use the ionic bond, because ionic bond is one party give, the other party take. And when you have two non-metals, both parties want to take. So ionic bond won't work. We need another mechanism, and that mechanism is covalent bonding. Let's start with the simplest example of covalent bonding, the bonding between two hydrogen atoms. Hydrogen has a proton number of 1. So it has only one electron in its outermost shell. So here we have a hydrogen atom with just one electron. And here we have another hydrogen atom also with one electron. Now they are both unstable they are both not perfect, not noble. They will want to achieve stability, nobility by bonding together. And they do so through sharing of electrons or covalent bonding. So they will come together, and they will share the pair of electrons that they have between themselves. So what you see here now is two hydrogen atoms coming together, sharing the pair of electrons they have, and so forming a covalent bond. This is the simplest covalent bond between two hydrogen atoms forming a hydrogen molecule. So what is covalent bond? Covalent bond is the electrostatic attraction of two atoms towards the commonly shared pair of electrons. Hi, let us now study the covalent bonding between two chlorine atoms to form the chlorine molecule. Now, chlorine has a proton number of 17, which translates to an electronic structure of 2,8, 7. So chlorine is just one electron short of the noble octet configuration. So to achieve the noble octet configuration, chlorine has to receive one more electron. So chlorine needs one more electron to become complete. Now, because covalent bonding at O level is always about equal sharing of electrons between two atoms, so if atom A contributes one electron, atom B must also contribute one electron. If atom A contributes 2 electrons, atom B must also contribute 2 electrons. In this case, since the first chlorine atom requires 1 electron from his partner, he must also provide 1 electron for his partner. Therefore, the chlorine atom needs to provide 1 electron for the bond. Now, 7 electrons minus 1 electron is equal to 6 electrons. So, having contributed 1 electron to the bond, the chlorine atom still has 6 electrons of its own. So now we are ready to draw the electronic structure of the chlorine molecule. First, we draw the 2 inner shell electrons. Then we draw the 8 electrons in the second shell. And let's draw the last shell, but bear in mind, in the last shell, 6 electrons are its own, 1 electron is in the bond. So we proceed to draw 6 electrons of its own, and we draw 1 electron within the bond. So on the other side, we do the same. We draw 2 electrons in the innermost shell, 8 electrons in the second shell, and this time round, similarly, we draw 6 electrons of its own with 1 electron in the bond. So this will be the full electronic structure of the chlorine molecule. Hi, let us now study the covalent bonding of 2 oxygen atoms to form the oxygen molecule. Now, oxygen has a proton number of 16, or should I say 8? And 8 translates to an electronic structure of 2, 6. So oxygen is just 2 electrons shy of the stable octet complete configuration of 2,8. So the oxygen atom needs just 2 more electrons to become stable noble octet. And because of the principle or our philosophy of equal sharing of electrons between the 2 atoms involved in covalent bonding, so if this oxygen atom wants to get 2 atoms from its partner, it must also contribute 2 atoms of its own, or should I say 2 electrons of its own. And in doing so, out of the 6 valence electrons, 2 electrons are being shared. There will be 4 electrons left of its own. So the oxygen atom in a covalent bond will have 4 electrons left of its own. So we can now draw the oxygen molecule electronic configuration. First, we draw 2 electrons in the inner shell, followed by 6 electrons in the outer shell, bearing in mind that 4 electrons belong to itself. 1, 2, 3, 4, and 2 electrons are involved in the bond. Next, we draw the other oxygen atom having the exact same configuration. So 2 electrons in the inner shell, followed by 4 electrons of its own, 1, 2, 3, 4, and then 2 electrons in the bond. So this is the complete electronic structure of the oxygen molecule. Hi, let us now study the covalent bonding between 2 nitrogen atoms to form the nitrogen molecule. The nitrogen atom has an atomic number of 7, which translates to an electronic structure of 2, 5. So the nitrogen atom requires 3 more electrons to achieve the noble octet configuration of 2,8. So the nitrogen atom needs 3 more electrons. Now, because of the concept of equal sharing of electrons between the 2 atoms involved in the covalent bond, for this nitrogen atom to gain 3 more electrons, it needs to also provide 3 electrons to the bond. Now 5 electrons, 5 valence electrons minus 3 electrons given to the bond, we are left with 2 electrons of its own. So in the nitrogen molecule, or rather when the nitrogen atom participates in the covalent bond, it would have 2 electrons of its own. With that, we can draw the electronic structure. So first we draw the nitrogen nucleus. We draw 2 electrons in the innermost shell, and bear in mind in the outermost shell we have 3 electrons in the bond and 2 electrons of its own. So 2 electrons of its own, and then 1, 2, 3 electrons involved in bonding. Now we do the same for the other side. So the other side, we have again 2 electrons in the innermost shell, and then in the outermost shell, same thing, 2 electrons of its own, which we draw here, and then 3 electrons in the bond, 1, 2, 3. So this is the full electronic structure of the nitrogen molecule. Now notice there are 3 pairs of electrons involved in the bond. So that is a triple bond. So the simplified diagram for the nitrogen molecule is 2 ends covalently bonded together by 3 covalent bonds, each line representing a pair of electrons. Hi, let us now study the covalent bonding in a water molecule between two hydrogen atoms and one oxygen atom. The hydrogen atom has only one valence electron, and so that one valence electron must be involved in the covalent bond. The oxygen atom has an electronic structure of 2, 6, and so it has 6 valence electrons, which means it needs 2 more electrons to become stable noble octet. And so because of equal sharing, it will need to provide 2 electrons to the bond or bonds, and 6 minus 2 is equal to 4. It will have 4 electrons of its own. So we use these knowledge to draw the hydrogen molecule. We start with the central atom, which is the oxygen atom. Okay, so we will draw the 2 inner shell electrons first. Now for the outer shell electrons, 4 electrons will belong to itself. 1, 2, 3, 4. And the other 2 electrons will be involved in bonding. And the hydrogen atom can be drawn here and here. So now you can count the number of electrons. For in the case of the oxygen, it has 8 electrons in the outermost shell, so it is now having an octet structure. And you look at the hydrogen atom, it has a duplet structure, which is also a noble gas configuration. So this is the full electronic structure of a water molecule. Hi, let us now study the covalent bonding in a carbon dioxide molecule between one carbon atom and 2 oxygen atoms. Now the carbon atom is the central atom. It has a proton number of 6 and an electronic structure of 2, 4. So carbon has 4 valence electrons. In order to achieve the octet stable configuration, it will need 4 more electrons. Now because of the principle of equal sharing, if this carbon atom needs 4 more electrons from its partner, it will also have to contribute 4 electrons to its partner or partners. Now 4 valence electrons minus 4 electrons contributed, so 4 minus 4 is equal to 0. So in the carbon dioxide molecule, the carbon atom will not have any electrons of its own. All 4 electrons will be involved in bonding. So similarly for the oxygen, let's look do the oxygen has a proton number of 8, which translates to an electronic structure of 2, 6. So it has 6 valence. It needs 2 more electrons, and so it will have to contribute 2 electrons, resulting in 6 minus 2 is equals to 4 electrons of its own. Okay, so now we can draw the electronic structure of carbon dioxide. First, carbon has got 2 electrons in the innermost shell, 4 electrons in the outermost shell, of which none of its own, and 4 involved in bonding, but since it has the bond with 2 oxygen atoms, each side will have 2 electrons. I repeat, 4 electrons involved in bonding to 2 oxygen atoms, so 2 electrons on each side. So for the oxygen atom, okay, it would have 2 electrons of its own, and in the outermost shell it would have 4 electrons of its own. So let's draw 1, 2, 3, 4, and then another 2 electrons in the bond. We do the same on the other side. Oxygen has 2, 6, so 2 electrons in the innermost shell, followed by 6 electrons in the outermost shell, but of which 4 are of its own and 2 in the bond. So this is the full electronic structure of carbon dioxide. Now notice there are 2 pairs of electrons in each covalent bond. So covalent bond is denoted by a single solid line. So each line represents a pair of electrons. So 2 pairs of electrons, 2 lines. So this is the simplified model of the carbon dioxide molecule. Hi everyone, let us now study the covalent bonding in an ammonia molecule. The central atom in this case will be the nitrogen atom. So the nitrogen atom has a proton number of 7, which translates to an electronic structure of 2, 5. So to become stable noble octet, nitrogen needs 3 more electrons. Because of the principle of equal sharing, to receive 3 more electrons from its covalent partners, it will have to similarly provide 3 electrons, a total of 3 electrons to its partners in the covalent bonding. Now 5 minus 3 is equals to 2 electrons of its own. So after contributing electrons to the bonds, you'll find that the nitrogen still has 2 electrons of its own. So let's now draw the structure. First, we draw the central atom, which is nitrogen. We draw 2 electrons that belongs to itself, and then we draw 3 electrons involved in 3 bonds with 3 hydrogen atoms. Next, we draw in the hydrogen atom, 1, 2, and 3. So this is the structure, the full electronic structure of the ammonia molecule. In simplified form, it will look like this.